respiratory system tonight. Yeah, you catch on every day I say this.
Yeah, I know.
Okay, can someone tell me what this is for? Do I have one?
Gas exchange.
I like that one better. Gas exchange. All right, let's review real simple thoughts. Which gases are you exchanging? CO2 and oxygen. Good, that took a while. Okay, which one do you want going in and which one do you want coming out during the exchange? CO2 comes out, right? O2 goes in. Pretty basic stuff, right? In and out of what? Was it? Nope. The blood. Ooh. So it's not about getting it in and out of your lungs, it's about getting it in and out of the bloodstream. The lungs are a mechanism by which you can do that. And then why do we want the blood? What's the blood for then? To transport, right? Once it's in my blood will take it throughout the body. So my goal of this system is to get the gases in the blood, and the blood takes it from there. Right? So it really isn't about the lungs per se, it's about the lungs and the blood coming together. So we're going to do that. So let's look at our pathway that thou shalt know. So here's Mullet Man. We're supposed to write down the organs in order that air would follow to get from somewhere to somewhere. So let's do the organs. You're supposed to know them in order you are. So let's start with one. Give me one up there somewhere.
Mouth.
Let's do nose. Let's pretend you breathe through your nose, okay? Let's pretend. So nose, I'm going to come out your nose in lab tomorrow. You'll learn this word, which is the pharynx, which is doctor speak for back of your mouth. What comes after a pharynx? Not yet. Larynx, which is doctor speak for voice box. Now you're in this tube. This tube is the trachea. So larynx goes to trachea. Also known windpipe. The trachea goes where?
Bronchi. Bronchus.
Bronchi. Bronchus is one. So bronchi. Okay? What comes after a bronchi? Bronchioles, which we'll leave off for today. What else?
Lung.
What is it?
Lung.
The lung. Very good. So the bronchi, put it in my lung, but we're not done yet. We're not. So we got to go a little deeper. So we're going to go inside the lungs. Boom. So here are my trachea, my bronchi of different levels. Those things in the corner. What are those? Alveoli, or alveolus is one, alveoli. So you're going to say alveoli. In English, those are air sacs, but you're going to say alveoli instead. Or alveoli and pretend they're ravioli. Right? But we're not done yet. So those are my air sacs. I'm not done because I got to keep going. So here's from lab tomorrow. This is a slide of your lungs. Those circles are the alveoli, the air sacs. But we're not done because I got to look at this picture here. What are those red things you see around those air sacs? Capillaries. Capillaries! Yeah! And what's inside capillaries?
Blood.
Blood. And here's now where you end. That's where you're trying to go, is the capillaries which contain the blood around the air sacs. So this is the goal, is to get to the blood capillaries that are around your air sacs. So it isn't to get it to the lungs, it's to get it to the blood that's around the air sacs. Make sense? So that's the goal, that picture. So I'm going to zoom in on that thing between the blood, the capillary, and the air sac. Okay? Zooming in right here. So I'm going to do actually this picture first. Here's a close-up showing air sac on the left, alveolus, blood capillary on the right. And here's that line between the air sac and the blood. That line is very important to know. Hint, hint. What do you call that thing between the air sac and the blood? Here. Right there. What is that? Respiratory membrane. So that respiratory membrane is an important concept. We're going to put it in green. That's between the alveolus and the capillary. That's the respiratory membrane. So when your book talks about the respiratory membrane, they mean between the air and the blood. That's where that is. That's the respiratory membrane. So tell me, do you want that to be thick or thin?
Thin.
Thin. So let's over here put some protocols with the respiratory membrane. Someone said you want it to be a thin membrane. So what kind of epithelial tissue would you find here?
Full squamous.
Simple squamous. Listen to that word. Okay, now the harder question. Why do you want it to be simple?
So you need the exchange to go through
To
quickly.
exchange, or Biology 112, thickness prevents diffusion. So a thin membrane allows more diffusion. It's easier to get from blood to gas and gas to blood. Right? So you want a thin membrane between your air sac and your blood. Simple squamous epithelial tissue. That ring a bell? Okay. Got some other characteristics. So I'm going to go to the bigger picture here. This is an alveolus. So this little ring is the respiratory membrane. There's a white thing in the corner and a green thing at the top. Let's do the white thing in the corner. What is that thing in the corner? Macrophage. What does that mean in English?
Big eater.
Big eater, it is. So a healthy respiratory membrane contain macrophages. So let's start with one of these. Oh, no, that one. So what's the job of a macrophage?
Eat things.
Eat things such as?
Big things.
Pathogen.
Aha, to eat pathogens. Okay, harder question. Why do we care about pathogens at your respiratory membrane?
So it doesn't get in the blood?
So they can't get in my blood, that's one choice. What else would happen? From last term, when you get something and breaches a barrier, what does your body do as a second line of defense? Learn this last term on your final. I can change your grade up to a year.
The T cells activate.
No, T cells have to come form.
What's it?
Inflammation, remind me what happens in inflammation. Increase fluid, right? Things get thicker and swollen. What would happen if your respiratory membrane got swollen?
You would be able to breathe your teeth.
I couldn't do exchange, right? The goal is it has to stay thin. So I don't want infections to start causing inflammation, irritation, scarring, because that would defeat the purpose of a thin membrane. So I have to protect the membrane from pathogens. Be macrophages. Make sense? Okay. Now another characteristic besides that is thin. Let's go to the other side. Let's find the green man. My favorite guy. Mr. Green. He is a surfactant secreting cell. Okay, so respiratory membranes have to have surfactant in them. Bonus smile if you actually know what surfactant means.
Lubricant?
Lubricant, a liquefier, very good. We'll call it lube for today. Why do your air sacs need lubrication?
So they don't stick together.
So they don't stick together. What would happen if your air sacs stuck together?
They care.
You couldn't.
They'd tear, they'd clump up, and what would happen to your ability to breathe if the air sacs are all clumped together?
You die.
You can't. So the goal of the surfactant is to keep the air sacs slippery and from sticking together. You can prove this at home. When I try to get the cling wrap off that little roll, the cardboard cutter doesn't work, right? It ends up tearing into 5 pieces, and they touch each other. What does my cling wrap do in the kitchen? Into a big ball, and then I cuss and throw it away and try again, right? Because there's no lubricant on the cling wrap, so it's sticky. It wants to stick to each other. So my air sacs would stick to each other if there was no lubricant, and therefore they would no longer be a thin membrane, right? So these are essential products of keeping the membrane functional between my blood and my air sac. Make sense? Okay, let's prove what would happen to you, or let's think about what happened to you if you're a smoker. Let's pick on smokers. They're always good to pick on. All right, so let's do some smoking. Ooh, not like that. That's good. Okay, so when you smoke, what does smoke do to surfactant cells?
Kills them.
Kills them. So now your air sacs are sticky. They clump together. What does smoking do to the white blood cells in your air sacs?
Kills them.
Kills them. Now you have nothing to keep infections out. What do membranes do when they're dry, sticky, and getting destroyed? They thicken, right? Which means they're no longer thin. So what happens to your respiratory membrane when you smoke? You destroy it. And what happens to you when this doesn't work?
You die.
You die. because the gases can't go from lung to blood and blood to lung because you destroyed those three things. Smoking will kill you because that stops. Right? Make sense? So for your lungs to work, this relationship has to be thin, moist, lubricated, and uninfected. Make sense? No matter what you smoke. Right? Make sense? That's the respiratory membrane. Okay, so now we have a problem. I know what's supposed to happen. How does the air know to go in from my nose to my blood? How do I get the air to go the right way?
Concentration.
Close. Let's talk about how you inhale. So we're going to do the steps of inhalation. I want to inhale and make the gases go in this order. All right? All right. There'll be 5 steps coming at you. Anyone tell me what the first thing you have to do to make gases go into your lungs? What was it? Say it loud. Move my diaphragm. Very good. So your diaphragm. Which way are you moving it? Up or down?
Down.
You sure?
Yes.
Positive.
Positive.
You're not going to change your answer if I keep asking? Most of you do. Okay. So the diaphragm will go down, which is called contracts. So the first thing I have to do is make my diaphragm go downward, contract, unbow. Okay. So what's going to happen to the size of my chest if the diaphragm goes down? Big, okay. So I'm going to increase your thoracic cavity. My chest gets bigger in volume. So my diaphragm went down, making my chest get bigger. Does that make sense? Okay, now here's the next jump. What do you think is going to happen to the size of your lungs inside this thoracic cavity? They're going to get bigger, so my lungs expand. My chest gets bigger, making my lungs get bigger. All right, next step, a hard step. What happens to the pressure inside my lungs when they expand?
Goes negative.
Increases.
We don't know. So if I make the lungs bigger, the pressure of air goes down inside. So the pressure decreases in the lungs, in the air sacs. So the pressure's going down inside my air sacs because I made the volume of the chest expand. Pressure goes down. So now let's go back to our mullet man. Your nose is the same pressure you started with. The lungs are now less. What did diffusion tell you in biology 112? High to low. So which way is the air going to go? The air goes in to your lungs because there's less pressure inside. There's more pressure outside. A difference of pressure gradient. So the air goes in because my lungs are less pressurized than before. Make sense? Okay, so I'm going to show you an animation of this process to prove I'm not making it up much. Okay, should be right here.
At the end of expiration, barometric air pressure and alveolar air pressure are equal. Therefore, no movement of air into or out of the lungs takes place. Inspiration begins with contraction of inspiratory muscles to increase thoracic volume.
What inspiratory muscle is he talking about? Diaphragm. So under normal conditions, your diaphragm is what determines breathing. So my diaphragm is the one that has to activate. You notice it's bowed to begin with, so it's going to pull or straighten downwards. So it's going to move downwards. That's going to change my chest cavity, which will change my lungs, which will change the pressure. Right? So I'm going to lower my diaphragm, which should expand my chest.
This results in expansion of the lungs and an increase in alveolar volume. The increased alveolar...
Just so you know, they're drawing as like you have one big air sac. Right? That's not anatomically correct, but you get the idea that all the air sacs would get pulled with the lungs so they'd all inflate. So you have one big lung with one big air sac and one big chest. Right? That works.
volume causes a decrease in alveolar pressure below barometric air pressure, and air flows into the lungs.
Okay, Okay, so the air outside didn't change, but my lungs now have a negative pressure. They're not a vacuum, they just have less pressure than before. So the air is going to go from high to low, more to less, so outside in, because my lungs are now less pressurized than before. Make sense? So the air is going in.
At the end of inspiration, the thorax and alveoli stop expanding. Airflow into the lungs causes alveolar pressure to become equal to barometric air pressure. Because the pressures become equal, no more movement of air occurs.
Right? Because there has to be a difference. So now I want to exhale. Can you guess what the first step of exhalation is going to be?
Relaxation of
Let's
the
find out. Then we'll write them on the board.
During expiration, the volume of the thorax decreases as the diaphragm relaxes and the thorax and lungs recoil. This results in a decrease in alveolar volume and an increase in alveolar pressure.
Bingo, let's put those steps on the board. Same number of steps. Tries. So we do exhalation over here. So for number one, for exhalation, what did my diaphragm do? It goes up or relaxes. So my diaphragm has to go up or relax. By the way, each step is the opposite. All right? So let's do the next one. So if my thoracic cavity got bigger in inhalation, what's it going to do in exhalation? It's going to get smaller. I'm pushing on it. So my thoracic cavity is getting smaller. I'm pushing on it with my diaphragm. So that's going to make my lungs do what?
Contract.
Get smaller or contract. So lungs are smaller. Okay? Then what should happen to the pressure if I'm squeezing on the lungs? Pressure should go up. So number 4. Pressure goes up in the alveoli. Because I'm squeezing on them. So if the pressure is now higher in my air sacs than in my nose, the air is going to go out. Number 5, air goes out. Right? So we'll finish the little animation, then I'll write 2 more things up. So if you can see, this is now showing the alveolar pressure is a positive number, so it's more pressurized than before.
Since the alveolar pressure is now greater than barometric air pressure, air flows out of the lungs. Air continues to flow out of the lungs until alveolar pressure becomes equal to barometric pressure.
So the way you remember this for your quiz next week is air gets pulled in, you pull the air in, and you push the air out. You pull it in, you draw it in, you push it out, you squeeze it out. So negative pressure inhalation, positive pressure exhalation. Make sense? Okay. Very good. Now I'm going to show you another animation of exactly the same thing with a little more detail to understand what we're going to do next. Okay? So exactly the same steps, nothing has changed.
Airflow in the human respiratory system is tidal, meaning that air enters the lungs by the same route that it leaves. The route inward begins at the nasal passages or mouth, passes through the pharynx, larynx, and trachea, and then through increasingly branched respiratory tubes, the bronchi and the bronchioles, before it finally reaches the millions of tiny air sacs, called alveoli, that make up the bulk of the lungs. The ability to inhale and exhale is based on the anatomy of the lungs and its surrounding structures. Each lung is surrounded by 2 pleural membranes. One membrane is firmly attached to a lung, while the other is attached to the wall of the thoracic cavity.
Remember from 231, visceral and parietal? That's that concept there. So the visceral on the lung, parietal on the chest. So there's 2 pleura, and there's fluid in between. The serous fluid, the pleural fluid is in between the pleural membranes and the pleural cavity.
Fluid fills the pleural cavity between the membranes. During an inhalation, the diaphragm and other chest muscles contract, causing the thoracic cavity to expand. The thoracic wall and its attached pleural membrane move outward, causing suction in the pleural cavity.
Okay, look at what he just said again. So I made my chest get bigger, I made my thorax get bigger. That pulled the parietal pleura away from my lungs. But because the same rule, I made the volume bigger, the pressure drops. That means the visceral pleura wants to stick to the chest still, so it moves along with it. If you go back here and watch that animation one more time. As I make my chest bigger, it's pulling on the pleural membranes, and they move out together. Right? So you go like this. There we go. Poof. And remember, the visceral pleura is on my lungs. So what do my lungs do when I pull my chest out? They pull out with it. So they work as a unit. I'm moving the chest to move the pleura, to move the pleura, to move the lung. But they all move as a unit because there's this pressure inside.
And its attached pleural membrane move outward, causing suction in the pleural cavity. The suction pulls the second pleural membrane along, as well as the lung to which it is attached. As the lungs expand, their interior gases also expand. The expanded air has a lower pressure compared to the air outside the body. Air rushes into the lungs to equalize the pressure. This is inhalation. When the diaphragm relaxes, the elasticity of the lungs causes them to recoil and push air back out through the airways. This is exhalation. Although breathing is an active process of muscle contraction followed by relaxation, air movement is passive. Air passively flows from regions of higher pressure to regions of lower pressure. During an inhalation, the pressure in the alveoli drops lower than the atmospheric pressure, and air rushes into the lungs. During an exhalation, alveolar pressure increases relative to atmospheric pressure, and air rushes out. This movement of air brings the alveolar pressure back to atmospheric pressure. The pressure in the pleural cavity is always negative with respect to atmospheric pressure. During an inhalation, as the chest expands, the pleural cavity pressure becomes even more negative, providing the suction to expand the lungs. During an exhalation, the pressure in the pleural cavity returns to its original value.
That makes sense? So the pleura are always pulling the lungs towards your chest. When I move my chest, the lungs have to follow because there's a suction between the two. That make sense? So what would happen if somehow the pleura didn't have that suction? What would your lungs do if the pleura couldn't hold them to your chest?
Collapse.
It would collapse, right? There'd be nothing to pull them out. Good, so now get out your packet of pain, because we're going to do just that. Find your lecture packet and turn to page 8. We're going to do this as a class. Don't have your lecture packet, just find someone who does. We're just going to do it as a class. Oh, not that one. Page 7. Sorry, not page 8. Wrong page. Back more. Sorry.